our blocks inside the furnace, resisting at 7 hours of 1800 Fahrenheit temperature.
Wait, 7 hours of 1,800 degrees Fahrenheit? Wow, that's very odd. I'm sure you could cook a pizza or even an egg in that. Oh yeah, you'd probably burn all of that. Well, that's a really, really hot temperature. How are they able to build materials that will withstand that? And moreover, withstand wildfires and fires, because that's a very big problem. Hi, I'm your host Akshay, and this episode, I'm going to take you into the science of these fire-resilient materials with the help of Dr. Michele Barbato. He studies fireproof materials and is working on making these fire-resilient materials at UC Davis in California, and he knows a lot about these fire-resilient materials that may be one day used to build fire-resilient homes. Let's get right into this amazing science. Hello, Dr. Barbato.
Hello, Akshay.
Thank you so much for joining me today.
My pleasure. Thank you for inviting me.
Yeah, thank you so much. So, can you please introduce yourself to listeners?
Absolutely. I'm Michele Barbato. I'm a professor of structural engineering and structural mechanics at the University of California, Davis. I'm also co-director of the UC Davis Climate Adaptation Research Center and the director of the CITRIS Climate Initiative. And very recently, I became also one of the co-champions for the Climate Grand Challenge at UC Davis. So a lot of climate.
Yes, a lot of climate. So, what was your team's motivation or driving question to build these special fireproof housing materials that we're going to talk about later in this episode?
Yeah, so actually, the story is a little bit longer than just the fireproof idea. We started working on earth blocks while I was a faculty in Louisiana State University down in Baton Rouge. And the question that we had was, can we build houses that are sustainable, affordable, and that can take what nature is giving to housing, particularly with climate change. We were very focused on hurricanes. I was a faculty there shortly after Katrina. There were a lot of people displaced by the hurricane, and we were looking for a new solution for housing that was able to sustain hurricanes, but also that was competitive in terms of costs. So we started investigating several different potential materials, and we started getting very curious about earthen materials because they were hitting all of the right spots. They were affordable, they were sustainable, and with appropriate design, they could take hurricanes, tornadoes. Then we investigated through a project with NSF how to design them for earthquakes. Then in 2018, I moved to California, to Northern California in Davis. And just a month and a half, 2 months after I moved here, we had the big campfire. And I just did 2+2. We have this material that has all of these nice properties, and we know that soil doesn't burn. So can we design houses that are also fire resilient with this material? And that's the research that we are doing right now. And the preliminary results are very, very positive.
Wow, that's really, really good. And it's glad to see that those results are getting there. We might get to true fireproof and these really resilient houses maybe sometime in the future.
So let me just clarify something. Fireproof is a very strong expression. Generally, we don't like to call a house fireproof because it's almost impossible to do a house fireproof.
Yeah.
What is fireproof is the material. So the walls are non-combustible and can be made fireproof. You still need to have a lot of care in all of the other details, doors, windows, vents, and all of that, because if embers enter inside a building, the inside cannot be fireproof. You have all of the things that are very combustible. So the walls are fireproof with this technology, but you need additional attention and other technologies to make the house really fire resilient.
Wow, that's a really good explanation of fire resilient versus fireproof. So, what are the fire resilient home materials that you're developing, and how did they work?
Yes, sure. So we are working on what is called compressed and stabilized earth blocks. If you are familiar with Adobe, is fundamentally an engineered version, a modern version of Adobe. We are making bricks with soil by adding a chemical stabilizer, typically cement or lime or a little bit of both. This stabilizer is really to provide additional resistance to weather and the water, which historically are a big problem with houses that are made just of mud. And then we are mechanically compressing it without any heat or without any additional energy applied to them to make it into something that is very strong from a mechanical point of view. So we get both the durability to weather and the mechanical strength that is needed for building not only houses, but also things like schools and other buildings that are one or two, maybe even 3, 4 stories, depending on how seismic the place where you want to build them is. So fundamentally soil. The large majority of the material is soil. Is soil that is taken a little bit deeper than the surface soil, because we want a material that has as little as possible organic material. So we don't want to have mixed with it wood, grass, that kind of things, because those are bad for the strength. And also topsoil is actually a very important resource for agriculture. So we go about 3 to 4 feet deep, and we use that soil to make our bricks. So fundamentally, the idea is with the right machine, you can make the hole that you would do for your foundations. And with that soil, you can pretty much build almost the entirety of your walls, at least for a one-story building. So that's the type of material, that's the process that we use to build it.
Wow, so you just compress that dirt and add a few additives, and then it becomes that fire resilient brick?
Correct.
So, how will these
So
bricks be arranged when you're building a house or a school?
well, you can use the same technologies that is used for any other type of masonry. Um, the difference is, instead of having the typical brick that is a fired clay brick or the typical concrete masonry unit, you're using our blocks that are made with dirt. We are also working on an additional technology that is based on using interlocking blocks without mortar.
Mm-hmm.
Fundamentally, these are huge Lego blocks made of dirt. And you get 2 advantages with that. One, it's faster, the construction, because the mortar phase is the one that is more time consuming. And also it's easier because now you have your interlocking elements exactly like the Lego block that make it so that you cannot put it in the wrong place.
Mm-hmm.
So it's a technology that I think has a lot of promise, because it reduces the cost, and it has other advantages that we are investigating.
Wow. So how do you test these fire resilient materials?
We did a few different tests. The most important one is fundamentally we put these blocks in a furnace with a certain time and a certain temperature. And then we test the mechanical properties before and after being in the furnace. And so with this technique, we were able to have our blocks inside the furnace resisting at 7 hours of 1800 Fahrenheit temperature,
Wow.
which is a pretty high temperature for a normal wildfires. In order to have higher temperature, you really need to have some house material and type things like gas or fuel that are burning. But typically, the wildfires is around that temperature, and our material resisted very well. Actually, strangely enough, the compressive strength of the material increased, which, if you think about it, makes a lot of sense. You transformed our dirt blocks into normal bricks because the clay cooked and they changed color. They became from brown, they changed it into red. So they had those properties
How much can it resist? Is it 1800 degrees Fahrenheit?
for 7 hours.
Wow. I think you could cook an egg on that, right?
Oh, yeah, 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 absolutely. I mean, it is not an ASTM standard, but typically, whenever we rate materials for wildfires, we're talking about a rating of 1 hour, 30 minutes, 2 hours, maybe 3 hours for concrete. This one goes forever.
Yeah, it
Um,
passes. It passes that limit.
I mean, I cannot say it because we didn't do an ASTM test for it, but all of the indications are very positive. Um, so we also push it to the limit, and we were able to glassify the material around 2200 Fahrenheit.
Wow.
Again, 7 hours plus at that time. Then what happens is that fundamentally starts melting and forming glass.
Wow.
Um, that I don't know if it is a specific value that is only for the soil that we tested. We used the soil of Paradise because of, again, the campfire. Paradise unfortunately was destroyed by that fire, and so we wanted to really find something that could be used locally to help people rebuild their community.
Wow, very nice. So, how much do these fire resilient materials cost?
So the material by itself is very cheap. The cost is fundamentally how much it takes for excavating it, which is obviously very limited in terms of cost. And also, um, it is easy to find a soil that works. So ideally, we are thinking about having the compression machine that is needed to build them go in loco and use the local material for building things. There are other possibilities like having actually a plant that makes the bricks and all of that, but you add the cost in terms of transportation. Um, so in terms of the base material, the cost is very small. The real issue in terms of why they are not widely used is that people are not very familiar with it,
Mm-hmm.
including building officials who have not really a lot of experience with the earth and construction in most of the cases, because 95% of the houses are built using wood here in the United States. And so they are usually considered some extraordinary material that requires additional controls, usually the signature of an engineer, of an architect. And so these type of things are making, right now, the houses cost more.
Mm-hmm.
And so typically there are two different types of structures that are right now built using this technology. Very expensive villas, multi-million-dollar villas, where the issue of getting someone to sign is not a big deal. And then very poor houses, often, unfortunately, not really designed, which is why for many people this type of material has a bad name, because when a structure is not correctly designed, it won't perform well. And we have a lot of examples of earthen constructions that have not performed well under earthquakes because they were simply not engineered to resist earthquakes. But I would say if you are building anything with any material, including reinforced concrete and steel or even wood, and you are not designing it correctly, they will perform poorly anyway. So it's not really a limitation of the material, it's more a limitation on how many people know how to use this material.
Wow, that's really so people just need to know that this material exists, and then more people will be aware of it, and more people will be able to use this for fire resilient homes.
That's at least the idea. And it's not only the owners or potential owners of the houses, it's also a process of education for engineers, for architects, for building officials. Like for all of the other materials, we need to build a community that knows how to build it, and we need to have enough builders that are willing to use this technology. There are very few builders around right now that know how to design and how to build this kind of houses. So that's also a difficulty. Even if someone wants to do it, very often they need to go to people that are several hundred of miles away from where they live, which is again one of the reasons of costs. But if the technology takes place and becomes bigger, then all of these type of costs will go down. And then we have shown that actually with proper design, the cost of these houses is very comparable with the cost of wooden houses. Similar type, depending on the place and on the local cost of labor, you could have something that is a little bit cheaper, like 2, 3, 5% cheaper, or 5, 10% more expensive. So the difference just in the structural side is not very significant. It's almost the difference of getting a luxury bathroom versus a normal bathroom. But your safety with respect to fires will increase a lot. And I suspect that also the insurance industry will catch up on that and will start considering the possibility of having these houses that are much more resilient to wildfires and probably try to have an incentive, an economic incentive for this type of houses. So when that will happen, I suspect that the community and the industry of earthen construction will really take place. Until then, it's going to be just a few houses here and there.
Wow, very interesting. So we have this earthen material. Now, what improvements are you working on, and what new technologies and materials are you working on for the future?
Yeah, so we are actually investigating several different options. On one side, we are working with the geopolymers to further improve the resistance of this material under high temperature and wildfires. So geopolymer, among the other things, has also the advantage of removing completely cement from the composition. The resistance to weather and water is obtained through other chemical processes than cement.
So what are these geopolymers?
These geopolymers are some materials where you add things like fly ash and other materials that contains a lot of silica with materials that are activating them, kind of salt type of things that are alkaline. And then they make these reaction that are fundamentally forming the same process in which rocks are formed.
Wow.
And so you generate from materials that are separated. They put you put them together and then they react chemically and they generate kind of a rock.
Wow, that's very interesting, and this is all just happening right now. Imagine what could happen in the future. Maybe we might have like entire houses or entire neighborhoods that will not be affected by fires, and we'll have everyone being safe from these wildfires and maybe even other weather events like tornadoes, hurricanes, or even tsunamis, which is just amazing to think about.
Correct. That's really the vision.
Yeah.
Having materials that are again sustainable because we need to reduce our effect on climate change,
Yep.
that are affordable because we need to make them available to everybody, and that are above all safe because we cannot continue seeing disasters on TV every single time something happens. And I'm of the opinion that there are no natural disasters. There are natural events,
Hmm.
and then the disaster comes when we are not planning for them.
Yeah.
So we need to plan for them. We need to acknowledge that they exist, that in some cases they are becoming worse because of climate change. And we need to change the way we do things so that we are less vulnerable to these hazards.
And
Another,
one thing that I really like about your material is that you'll never run out of dirt, hopefully, in the near future,
correct.
but you will not run out of the soil that's in the ground. So it's truly sustainable. It's truly sustainable in this world, especially with all this climate change and talks of sustainable energy, sustainable fuels, all that. This just meets that category.
That is correct. It's extremely readily available almost everywhere and is plentiful,
Maybe not
much
in
more than
Antarctica though.
any other construction material we can think of. Also, typically, the mining operation is significantly simpler because, again, you are not going very deep to find appropriate soil. You just need to make a hole that is 3 to 4 feet deep, and then you start picking it up. Much easier than in many other mining operations where you have to use explosives or you need to make very deep holes in the ground. This one is easy.
Yeah.
And
That
I wanted to add one thing to your previous question. Another thing we are working on is using 3D printing for this type of materials.
wow.
Um, this one is not only for applications on our planet, but this is also a little bit more futuristic. We are really thinking of how are we going to inhabit other planets like
Hmm.
Mars or even just the closer moon, where you cannot really bring a lot of material from Earth. So you need to use the local material. And obviously, earthen material is similar to Martian material. So we have been doing a little bit of Martian blocks, the first Martian blocks, and we are using 3D printing for this kind of applications that are valid on our planet, difficult to reach places or dangerous places, and on other planets if we ever end up building anything on those planets. So,
Yeah, very interesting. This is very interesting. So now, moving on to the next generation, what advice do you have for kids who are interested in science? Maybe you want to develop your technology that you're developing now even further.
and The thing that has always pushed me was curiosity, learning how things work and why, not only what they do, but why they do the way they do it. And I think that's really the skill that you want to exercise as much as possible is your curiosity. With curiosity comes everything else. The other thing is, and probably this may seem cliche, but follow your passion. A lot of people sometimes try to go into studies because they think, oh, this is paying better. And what I tell always my students is, in your life, you have 24 hours per day. You're spending 8 hours working, 8 hours sleeping. The other 8 hours, you don't want to spend them doing something just to forget how miserable you were during the 8 hours you were working. So you need to find something that you enjoy doing, you're good at, and that can also pay your bills at the end of the day. But if you miss one of these three, your life will become much harder. So
Yeah, very great advice. Just follow your passion and stay curious. That's some very, very great advice. Thank you so much for your time today. I really enjoyed it and I learned so much about your fire resilient homes. I shouldn't say fireproof because you're not truly fireproof. Fire resilient homes
correct.
and how these technologies are evolving and how they could in fact help humanity in the future and help us stay sustainable.
Thank you for inviting me. It was a pleasure. And I
Yes.
hope that everybody who will see this podcast will enjoy it too. And
Mhm.
we definitely need all of the new generation to continue on the path that we are starting to take now toward a more sustainable future and a more just future for everybody. So I have a lot of hope for the younger generations. That's one of the reasons that I am a professor, because of this continuous contact with the younger minds and younger people and their enthusiasm, and so it was a pleasure for me to be here.
Yeah, thank you so much. Thank you so much for listening to this episode of Spectacular Science. Spectacular Science produced and hosted by me, Akshijit Raman. Our theme song additional music are by Charan Ramachandran. Special thanks to Dr. Michele Barbato. Thank you so much for your time and I learned so much in this interview. Please visit my podcast website, spectacularsci.com, to find interactive activities, articles, and blog posts. That's spectacularsci.com. Do you have a science question you want answered on a new Spectacular Science episode? Well, grab a parent and head over to spectacularsci.com/contact to send me your amazing science questions. Thank you so much. I'm looking forward to answering your amazing science question on some of these upcoming episodes. Also, don't forget to subscribe to Spectacular Science wherever you're listening right now. It really encourages me, and you'll be up to date on all the new episodes. Subscribe and share this podcast with your friends and family. Thank you so much. Thanks for listening, and we'll see you on the next episode of Spectacular Science next week. Keep thinking about science.